So this is the frequency response of this new filter. So we are once again using FracZ from SciPy. Here, this is the filter we obtain from the C coefficients if we don't replace the delays by all passes. Yeah? Here we can see that in the warp domain we obtain a reasonable low pass filter. So in the pass band from 0 to somewhat above 1.6, it has a drop of about 10 dB, and in the stop band we obtain minus 30 dB attenuation, which is much more than before, but it might still not be enough for practical purposes. So now we use the same coefficients, but now we will replace the delays in the FIR filter with all pass filters. So in this way we go from frequency response HZ to H warped of Z. That will be the H of all pass filters given by this equation here, and it will look something like this. So what we do is we have here the warping all pass filters. We have the numerator and the denominator. We'll calculate the impulse response. X is the impulse response. Now we will have our warped delays. So we will take this X and we will filter with this numerator and denominator using the whole filter from SciPy signal. So we will have y1 here, then y2 will be the y1 filter with this numerator and denominator. We have y2 here, and then we will have y3, and then the output of the warped filter, it will be the C0 times X plus C1 times Y1 plus C2 times Y2 plus C3 times Y3. So this is the procedure we had before these coefficients C from here, filter coefficients in the warp domain, but now we are replacing the FIR delays by all passes. So what we're doing, we're defining here the warping all pass filters, and then we are doing this X times C0 plus Y1 times C1 plus Y2 times C2, and here is our all pass filters. Then the output is given by this, the sum of all these, the Y of n, and we can see the frequency response of this filter now, and this is the frequency response of our final warped low pass filter. We can see again that we have a drop of about minus 10 dB in the pass band, now from 0 to 0.05 pi, and the stop band attenuation of about 30 dB, which is somewhat reasonable. We can see the impulse response of this filter here if we plot the Y out. We compute it from here, and it looks like this. This is the resulting impulse response of our warped filter. What is most obvious is its length. Instead of just 4 samples as our original unwarped design, it easily reaches 80 significant samples, but it's in principle infinite in extent. So this is also what makes it a better filter than the unwarped original design. You can take a look at this paper which I mentioned before, and also a paper by Professor Schuller, frequency warping in low delay audio coding, and you have good examples and explanations of this type of design.